Hey everyone, Dan here with a practice problem on buffers and how to determine the pH change if you add an acid or a base to a buffer solution. Before we get into the problem, let's briefly review what a buffer is. So a buffer is going to be a solution made from either a weak acid or a weak base and a conjugate of that weak acid or weak base. So in this case, I've drawn the equilibrium reaction of a generic weak acid, HA, and it's reacting with water to form hydronium and the conjugate base A-. You'll notice that I have written HA and A- very, very large. That's to indicate that we want we want a bunch of weak acid and a bunch of the conjugate base present in that solution in order to increase the buffering capacity of the solution. So let's imagine that we take this buffer solution and we add a strong acid to it. So I've just selected HCl as my example for a strong acid, and we know that strong acids are going to react with water to form hydronium and the conjugate base. We also know that strong acids react completely, so you'll notice that I've drawn a single reaction arrow, so it's going to go all the way to product. So notice that if we have a buffer made from a weak acid and we add a strong acid to it, we're going to dissociate to form a common ion. So when we dissolve this acid in water, we're going to increase the amount of hydronium present in solution. And when we do that, we're effectively adding a product to this equilibrium. So if we think about Le Chatelier's principle, if we increase the concentration of this hydronium, we are effectively going to push this reaction back to reactant. And in the process, we're going to increase the concentration of our weak acid and decrease the concentration of our conjugate base, because this reaction is going to be running in reverse to compensate for this additional hydronium. So what's going to happen is, if we represent this graphically, notice that the concentration of A- went down and the concentration of HA went up. So that's how it's going to compensate for the addition of an acid. If we add a base to this instead, notice we have the same equilibrium up here. If we add a strong base, such as sodium hydroxide, that's going to dissociate completely into Na+ and hydroxide ion. And hydroxide ion is going to react with the acid and is going to neutralize that acid. So we have, for every OH-, we react with one of our weak acid molecules to form water and some of the conjugate. So notice if we add hydroxide ions, we are effectively going to decrease the concentration of our weak acid and increase the concentration of our conjugate base. So we can represent that graphically as down here. We've decreased our concentration of HA, we've increased our concentration of A-, and in the process we've kept the concentration of hydronium relatively constant. So that's how it's going to regulate pH if you add a base. Alright, so with that out of the way, we can start to take a look at question 8. So this is the question 8 from the buffer review questions, and the question reads, a buffer solution contains 0.51 molar ammonia and 0.49 molar ammonium chloride. The pKb of ammonia is given, and that's at 4.75, and our first task is to determine the pH of the initial solution. So before we add any strong acids or strong bases, we just want to know baseline, what's our pH. So to do that, you've probably done a million of these already, but we're going to do an ice table, and notice I've just put in this reaction of ammonia reacting with water in equilibrium with hydroxide ion and ammonium ion. So we were given our initial concentrations for ammonia and ammonium, and I put those in the initial line, 0.1 or 0.51 and 0.49. We're going to assume that the initial concentration of hydroxide is low enough that we can just say that it's negligible, so that's about 0. And then we're going to say, all right, this reaction's, we're going to assume that it's running in the forward direction, so we have a minus x, a plus x, and a plus x for our change in line. And then equilibrium is just going to be the sum of those first two lines, so we have 0.51 minus x, x, and 0.49 plus x. And we're eventually going to set up a KB expression, but notice we weren't given the KB, we were given the PKB. So first we have to undo this negative log, and so to get KB, we're going to do 10 raised to the power of negative PKB to get a value of 1.778 times 10 to the minus 5. So now that we have our KB, we can set up our KB expression, which is going to be the products over the reactants. We're not including water because that's a liquid. And when I substitute in our equilibrium concentrations here, we have x times 0.49 plus x divided by 0.51 minus x. And what we're going to do to make our lives a lot easier, since we know that the value of KB is very low, we are going to assume that the plus x and minus x are small enough that effectively these concentrations really aren't changing. So we can simplify this expression by getting rid of the plus and minus x, and then that leaves us with x times 0.49 divided by 0.51. We set that equal to the KB that we found in the previous step, and then we can solve for x, which in this case is our equilibrium concentration of hydroxide ion. So if we solve for x, we wind up getting a value or a concentration of hydroxide of 1.85 times 10 to the minus 5 molar. And since we did make an assumption here saying that the plus and minus x's were negligible, what we want to do is just real quickly run through an assumption check to make sure that that's valid. Basically, in order for the plus and minus x assumption to be valid, your change in concentration has to be less than 5%. So what we want to do is put our calculated value of x over the smaller of the two concentrations. So if we go back up to the ICE table, our initial concentration for ammonium was slightly smaller. So we're going to use that down here. So we have our x value divided by the initial concentration of ammonium times 100, and that's going to give us a percentage. So we have 0.0038%, and so any value less than 5% is okay to make that assumption. So obviously 0.0038% is much less than 5, and so this assumption is valid. All right, so with that assumption check out of the way, we are free to proceed to the next step, which is going to be we want to find the pH. So remember that pH is the negative log of the hydronium concentration, and we actually have the hydroxide ion concentration. So in order to get the hydronium concentration, what I'm going to do is substitute my values into the Kw expression. So we know that Kw is the concentration of hydronium times the concentration of hydroxide, and at 25 Celsius, that is going to be equal to 1 times 10 to the minus 14. So if I rearrange this and solve for hydronium, we wind up with a hydronium concentration of 5.40 times 10 to the minus 10 molar. And now that we have this, we can simply take the negative log of that value, and we get a pH of 9.27. So the pH of the original solution, before we add any acids and bases, is going to be 9.27. So keep that in mind. We're going to compare that value at the end to the pHs that we get in Part B and Part C. And hopefully, if the buffer is actually working appropriately, that pH won't change very much. All right, with that said, let's proceed to part B. So now what we're going to do is we want to determine the new pH of the solution after we add a certain amount of hydrochloric acid. So we're adding enough to make a new concentration, or enough to make 0.15 molar HCl, and we're going to assume, just to make our lives easier, we're assuming that there's no change in the total volume. So keep in mind that when we add a strong acid, that acid's going to react completely to form hydronium and the conjugate base. We don't really care about the conjugate base in this case because the Cl- doesn't appear anywhere in our reaction, and so what we're really concerned with is the hydronium that's produced when we dissolve this acid into our solution. So if we started off with 0.15 molar HCl, all of that HCl is going to react, and so if we do some dimensional analysis, we can figure out our new concentration, or our concentration of hydronium at the start of this reaction. So 0.15 moles HCl per liter, this reacts to form, we have a 1-to-1 molar ratio here, so I set that up here. So solving for the concentration of hydronium, we get 0.15 molar hydronium that we've added to this buffer. So now let's think about what happens when that hydronium reacts. So we have a buffer that's composed of a weak base and the conjugate acid. And so what we want to do is think about, all right, if we add an acid to this, effectively what we're going to be doing is neutralizing the base. So when we add our acid in, we will be consuming the ammonia and producing some ammonium. And so what we're going to do is assume that we have 100% reaction of that strong acid, and when we do that, we're going to set up a kind of a funky ice table. So it has the same form as an ice table, but really what we're doing is we're figuring out how our concentrations are going to change of our for our buffer components, so the weak base and the conjugate acid. And we're going to assume that all of the hydronium that was present at the beginning is going to react, and along with it, we're also going to change the concentrations of ammonia and ammonium. So if we start with 0.15 molar H3O plus, all of that is going to react, so our change in line is going to be minus whatever is in your initial line here, and we're going to get an equilibrium concentration, or a final concentration, for hydronium of 0. And so when we carry that change through for all of our components, we're going to consume 0.15 molar ammonia, and we're going to produce 0.15 of ammonium. So this final line is going to give us our initial concentrations for when we set up our regular ice table. So now what we do is we're going to carry these numbers through and set up a normal ice table with our original reaction here. So we have the ammonia, water, hydroxide ion, and ammonium. And then we're going to plug in those new concentrations after we factor in the reaction with the acid. So what was left over after that acid completely reacts with the buffer solution is 0.36 molar ammonia. Again, we're going to assume, just like normal, that the initial concentration of hydroxide is about 0, and then our ammonium concentration actually increased, and it's now 0.64. So just like a normal ice table, from here on out, basically this is a normal ice table problem. Again, we're going to say minus x, and plus x, and then the equilibrium line is just the sum of the first two lines. So now that we have these new equilibrium concentrations, we can plug those numbers into our Kb expression just like we did in part A, and we can solve for x, and in this case we wind up with a concentration of 1 times 10 to the minus 5 molar. again, we've technically made that assumption here that plus and minus x are negligible. So I'm going to run through a quick assumption check again. And in this case, you'll notice that the component of the buffer that I'm using to check the assumption actually changed. So in part A, I used ammonium because that was the component that was in the lower concentration. In this case, since we've used up some of that ammonia, I'm actually going to use this number because 0.36 is lower than 0.64. So I'm using ammonia down here. So x divided by the ammonia concentration times 100 has to be less than 5%. So we plug in those numbers here, multiply by 100, and we get 0.0028%, which again is much lower than 5, so the assumption is valid. With the assumption check out of the way, we can do exactly what we did before, change our hydroxide ion concentration into a hydronium ion concentration using Kw, and we get a hydroxide ion concentration of 1 times 10 to the minus 10 molar. And so taking the negative log of that, we get a new pH of 9. So we see that compared to the original value of 9.26, it has decreased. So it's gotten a little bit more acidic, which makes sense because we've added an acid. But the pH hasn't changed very much. If we had just added that 0.15 molar of hydronium to pure water, our pH would be way, way lower. So we've shown here that the buffer is actually compensating for the addition of the acid and resisting that pH change. All right, so that's how you would do this problem for the addition of a strong acid. The next step is going to be, all right, what if we added a strong base instead of a strong acid? So we're going to assume that we have the original solution again, so before we added that acid in the last part, and now instead of that we're going to add calcium hydroxide. So we're adding enough solid calcium hydroxide to make a concentration of 0.10 molar, and we're going to again assume that there's no change in total volume. And keep in mind that when we dissolve this calcium hydroxide, we're actually going to produce 2 equivalents of hydroxide ion. So if we take this balanced chemical equation, for every 1 mole of calcium hydroxide that I put in, I'm getting out 2 moles of hydroxide ions. So if we real quickly convert from molar calcium hydroxide into molar hydroxide, we can see that we actually have essentially double the concentration of hydroxide ions relative to the concentration of calcium hydroxide. So what we're again going to do is assume that we have a 100% reaction. In this case, since we started off with a buffer that was made from a weak base, when we add a strong base, notice that they have that common ion. They both have the hydroxide ion. So it actually makes your life a little bit easier. You can use the same equation. You don't have to rewrite it in terms of like in the last one where we rewrote it with hydronium instead of water here. Instead of water here. And so basically when we do the funky ice table for the addition, what we're going to do is just put that 0.20 in here. We're going to put the initial concentration that we started with back in here for ammonia and ammonium. And in this case, if we've added something to the product side, we're going to push that reaction back toward reactant. So again, we're going to assume that we have a 100% reaction. So whatever we started with here for hydroxide ion, we're going to say all of that is used up. And so our equilibrium concentration, or our final concentration for hydroxide ion, is going to be 0. And then everything else has to change according to how much this changed. So we're running in reverse, meaning that ammonium is going to be consumed. So that's going to be a minus 0.2, just like the hydroxide ion. And ammonia is being produced, so this is going to be a plus 0.2. So when we add and subtract those values, we get final concentrations for ammonia of 0.71 and a final concentration of ammonium of 0.29. And now what we're going to do is use those new values as our initial values in the regular ice table. So after the complete reaction with that strong base, we have an initial concentration of ammonia of, again, 0.71. We're going to assume that hydroxide ion concentration is about 0, and then for ammonium, we have a new initial concentration of 0.29. All right, so the rest of this is just pretty much identical to the last two steps, or the last two parts of the problem, where we're just setting up a regular ice table. We're assuming the reaction runs in the forward direction, so we have minus x, and plus x. Again, equilibrium is just the sum of the last two lines, so 0.71 minus x, and 0.29 plus x. All right, so throwing those values into our Kb expression, we get a value of x, which again is the hydroxide ion concentration, of 4.35 times 10 to the minus 5. We'll do a quick assumption check again. Notice I'm using ammonium this time again, because ammonium is present in the lesser amount. And so we have our x value divided by ammonium times 100, and that gives us a percentage of 0.015%, which is still less than 5%, so the assumption is still good. All right, so again, what we're going to do is just convert this hydroxide ion concentration into a hydronium concentration. When we do that, same setup as before. When we do that, we get 2.3 times 10 to the minus 10. And if we take the negative log of that value, we get 9.64. So again, just like in part B of this problem, where our pH just went down a little bit, now our pH has gone up a little bit, which again makes sense because we're adding a base. We would expect the pH to increase, but the buffer effectively resisted that pH change, and so it didn't increase by very much. So 9.64 is not much higher than 9.26, I believe it was. 9.27. So 9.64 versus 9.27, relatively small pH change. All right, so that is basically it for buffer problems where they have you add a strong acid or a strong base to a buffer, and then they want you to figure out the pH change. The trickiest part really is wrapping your head around this weird ice table. So just always treat it as you're assuming 100% reaction of either the hydroxide or hydronium that you have here, and you're targeting a 0 here, and then everything else just has to change accordingly. At that point, once you have your final values, you can just plug them into a normal ice table, and then it's off to the races. All right, that's it. So if you have any questions, please either come to office hours or send any of us an email, and we can help you through it. All right, good luck, have fun.